Need to be live. I'm live. Okay. So let's fire this up. Get full screen. Okay. So today we're going to keep talking about Bayesian principles, contrast them a little bit more with other principles, and continue building on what we said last time. Perhaps most importantly, that we are at Columbia. Columbia develops stand, a use stand, and a division to developing stand. That creates the appearance of a conflict of interest due to private interests, such as whatever led them to feature stand on billions. Okay, so we were talking about the beta posterior distribution that could be obtained in more or less closed form. It's an exact beta distribution if you have beta prior distribution over the survival probability combined with the binomial likelihood for the survival probability evaluated at the observed number of successes, which in this case was 5 survivors out of 7 people with Ebola who had been given this experimental drug. We talked last time about prior predictive matching as a way to draw from the posterior distribution. Wouldn't be necessary in this case because you can simply draw from the beta posterior distribution. But if you were using a different prior distribution with the binomial likelihood, you could still obtain draws from the posterior distribution via prior predictive matching. And if you think about that a little bit, it illustrates that the posterior distribution, or the PDF of it that we obtained, is the function closest to the prior PDF that satisfies a constraint given by the observed data. So in a manner of speaking, the posterior PDF is a solution to an optimization problem. However, it is not the sort of optimization problem that you see most commonly in the social science and otherwise. So in this case, it's the optimal function. Whereas usually when we think of optimization in the social sciences, it's to find the optimal point or set of points if it's a vector. In this case, with a one-dimensional posterior distribution, we can verify that the posterior expectation will be between the prior expectation and the sample mean. So here I chose as my hyperparameters a equal 3, b equal 2. Those had to be positive, but they didn't have to be integers. That implies a prior expectation on the survival probability of 0.6, which may have been reasonable. In actuality, 5 out of 7 survived, so the sample average is 5/7. And the posterior expectation under the beta distribution is given by the expression in the middle, and it comes out to be 2/3. And so this seems like a comforting fact to many people that the posterior average is between the prior average and the data average. However, this is one of these things that seems and is intuitive in one dimension and ceases to be correct, or the intuition of it does not extend to the case where you have multiple parameters, because for multiple parameters, it's not well defined for them to be between, something and something else when you're talking about 2, 3K dimensions. But in any event, the posterior distribution is influenced both by the prior distribution and by the likelihood. You can also see from this expression that if you have a lot of observations keeping A and B fixed, then the posterior mean is going to converge to the sample mean, so the influence of the prior dissipates as you have more data. And it wouldn't matter if the data arrived all at once or one observation at a time, somewhere in between. You could update this with one data point n times, or you could update it once with n data points. In the end, you're going to end up with the same posterior distribution, and in this case, that is beta with first shape parameter a star being a plus y, and b star second shape parameter being b plus n minus y. I did not have enough volume this whole time. Okay, now can you hear me? And that contains all the information available from past data. So beta prior binomial likelihood is example of natural conjugacy in the sense that if you start with a beta prior and condition on binomial data, then you're going to get a posterior distribution in the same family, but with different hyperparameters, A star and B star, rather than A and B. And so you can get essentially exact posterior distributions if you use conjugate priors. That is very useful in formal models. It's not so necessary for the past several decades, because you can do what we'll learn about next week, and in particular we can do Stan. But decades ago, this was essentially the only way you could do Bayesian inference, and it was limited to a handful of combinations of like likelihood and prior, usually with a one parameter model where you're able to get an exact answer. All right? So once you have the posterior distribution, whether that's draws or whether it's exact, if it is exact, you can always draw from it, and that allows you to obtain draws from the so-called posterior predictive distribution, which is just like the prior predictive distribution, except you're starting with posterior draws. So the three steps are: you draw the parameters from their posterior distribution. This will usually happen, all at once. But then you condition on each of those draws from the posterior distribution to draw a realization of the outcome from its conditional distribution that you could then store. And those draws of y tilde constitute what you would predict future y to look like given your updated beliefs about the parameters. And so those draws of your predictions for future y have a PDF that can be expressed like this. So this is a density function for future outcomes, conditional on past outcomes, and whatever prior information you put into it, can be thought of as the integral over the parameter space of the conditional distribution of the data given the parameters, weighted by the conditional distribution of the parameters given past data y. And if you multiply those two together, you get a bivariate density between future data and the parameters theta that, if you integrate over the space of theta, yields a posterior predictive distribution for future observables conditional on past observables and whatever went into your prior. So this I refer to, no one else does, as the Bayesian hokey pokey, because you sort of take this density that you want, you put in theta, which are the parameters, and expand it as a product, and then you integrate theta out, leaving you with the density that you wanted. And this you can use to make predictions of future observables, which brings me to a point that I may not have emphasized that much previously. Supervised learning is definitely geared toward predicting future data, and you can do that with the Bayesian approach. And it's in a way better because you get an entire distribution of predictions for each future data point rather than a single prediction. And so you can incorporate your uncertainty in making those predictions into the decisions that you need, estimates of future data in order to make, particularly when doing like finance and stuff. The uncertainty dictates how much you hedge, for example. If the posterior distribution is exact beta, then this integral can be more or less solved in terms of a special function yielding a posterior predictive distribution that is the so-called beta binomial probability mass function. You've got to choose y tilde out front, and then the ratio of two beta functions there. That is a valid PMF known as beta binomial, and that is the density that describes your predictions of future people who, if they get this drug, given the past people who did and whatever prior information you put in. Remember, all of this stuff where you integrate out the parameters it doesn't mean you're making like model-free inference. You're just saying under the model, but irrespective of the parameters, here are my predictions of the observables. And this three-step process is basically the same as prior predictive distribution, except you're using posterior draws in step 1 rather than prior draws in step 1. Good? Okay. So in Lancaster, there's a footnote that has this quote from Fisher about the object of statistical methods, and Fisher claims it's the reduction of the data. Data by its mere bulk is incapable of entering the mind, is to be replaced by relatively few quantities which shall adequately represent the whole, ideally with all the relevant information contained in the original data. And that is a fairly unequivocal statement that almost everyone else would disagree with. Well, not everyone else. There's a lot of people that Fisher convinced. But there's a lot of people who would completely disagree with that. Notably, Fisher's, let's say, colleague, an enemy, Neyman, who would say, well, the object is to implement decision rules that have good properties across all the decisions we make. Bayesians clearly object that the object is to update your beliefs about the unknowns. Econometricians, who sort of, depending on how you count, started around in the 1940s, would not have agreed. Usually the object there is to figure out what some equilibrium is among optimizing agents, but econometricians sort of developed their techniques kind of in parallel to statistics over the latter part of the 1900s. Supervised learning, as I mentioned before, there the object is to predict the future. And basically everyone who's doing applied statistics from a scientific standpoint these days is trying to estimate, at least ideally, the causal effect of something. So it's not the mere reduction of data in order to have a few quantities that capture all of this information. But that's what it meant to Fisher. And I think it's good to think of all the quantitative techniques that Fisher introduced in light of this stated goal. And that being different than the stated goal of certainly everyone today, but also a lot of people in the past. So here's an example of that sort of reduction, but tying it into some of the stuff that we did on Tuesday. So the US government has data on household income, and in 2018, the 20th percentile was 25,600. The median household income was 63,179, and the 80th percentile of household income was $130,000, or at least these were estimates from the surveys the government did. And so household income can't be negative. So this is a distribution that only has a bound on one side at 0. In theory, it could be infinite, even though no one has infinite income. But a quantile parameterized distribution that would be consistent with the above facts is given in the same paper, the name Johnson quantile parameterized distribution of a semi-bounded random variable, so it ends with S rather than B. And we can do that in much the same way, compile those quantile functions that I wrote for you, call the vectorized function, so that this is easily callable on R with a vector of cumulative probabilities, and then we call this. Only difference, instead of having a bounds argument that is a vector of size 2, we just have lower bound as a scalar, 0 in this case. Also, we have the 20 percentile and the 80 percentile, so I specify alpha equal 0.2 rather than alpha equal 0.25, which we did previously, but that's still fine. I give it my 3 values, and I can plot that curve where we have the cumulative percentage of people who have income less than or equal to any value along the horizontal axis here. And on the vertical axis in log scale, we have the implied income for that household. So you can see again, if you go point 2 up to here and then across to the thing, that is going to be exactly 25,600. And the same with the median, the same with the 80th percentile. So we have an increasing function that runs through our 3 points, but in this case we just have the bound from one side rather than both.
Maybe I missed this the other day, but for the 3 quantiles that we specified, does it always have to be the median, some alpha, and then 1 minus the alpha?
Yes. Other questions? Right. So here, even though we might use it for a different purpose, we've done a Fisher-like thing. I don't know how many households there are in the United States, probably over 100 million. So rather than thinking of like all of those points or whatever sample of those points the government used to come up with these things, we've just replaced it with like 3 numbers and a function that runs through those 3 points. And so now we have, instead of like all this data, we have this one function that we can query, and it is like a more or less pretty good approximation of the actual income distribution. And so if we wanted to calculate the mean income, we could do that. And if we wanted to do something with like individual data points where maybe we didn't have an analytical solution, we can just simulate from this distribution by drawing uniformly along the horizontal axis up to the curve projected over to the vertical axis, and now we have draws of income that, essentially in probability correspond to draws of actual households. And so we can do our calculations point-wise if we wanted to, scaling up or down the number of points as necessary. So this would be an example of reducing like the complicated, bulky data on US households to a function that just has 3 knobs that we can twist or specify in order to define a particular increasing function from the 0-1 interval to the positive real numbers interval. Yes?
What I don't understand is like, why is this better than what I imagine normally econometricians would do, where they would have just like some linear model? They would have a straight line. Like, why is this a better?
So economists would often fit models to log income, predicting a particular household's income as a function of their characteristics. So here we're not conditioning on any aspect of the households. This is just the marginal distribution of income in the United States. If like income was missing on some people, you could use this to impute their income, but you would probably want to do some conditioning to predict where along the horizontal axis that person would fall. So if it's something, someone who like didn't even have a high school degree or whatever, you're gonna, tend to predict them farther to the left. Someone who has, at least a college degree or business school degree or whatever, much more to the right in terms of where you would impute their income from.
Maybe I'm thinking about this wrong, but how does this work in cases where there's like a lot of income inequality, where like the top is a lot more, people make a lot more money? How would this curve kind of fit?
So I should say that this approximation of the income distribution might not be good enough for you if what you're really interested in finding out about is the extreme upper tail. Because we've only basically pinned this curve down based on 20th percentile, 80th percentile, and median. And so if you were worried about the top like 100th of 1%, then maybe the tail of this is not exactly right, because none of those influence the 3 points that you ran the line through. But for the bulk of people, this would be a reasonable approximation. And if we were sort of interested in sort of upper middle class to lower class income inequality, then if the 80th percentile was 200,000 and the 20th percentile, which is like more or less the poverty line, were let's say 20,000 or something, that would represent more income inequality than what we actually think took place in 2018. So, but if you're really interested in sort of like CEO inequality relative to like typical worker inequality, then you would want to probably have a separate distribution for the extreme tail, like top 1,000th of 1% people. Because, that's, here we're running into like 300,000, so maybe like doctor territory, but not Jeff Bezos territory. Anyway, so, but if we can do this for like observable data, we can also use the same process to describe our beliefs about parameters before we see the data, and use that as like a prior transformation, assuming a standard uniform prior along the horizontal axis and this transformation. Okay, so I want to put some tips to avoid being confused by frequentist statements and whatnot, which I think is important because it is true, I think it's not too controversial, although I guess it's just my opinion, that a lot of the persistence of frequentist techniques and thought and whatever is sort of exploiting people's confusion about it. And it might be less commonplace if more people were less confused. So number one tip to avoid is figure out what is the nature and the timing of the randomization that kicks off the whole need for probability in the first place. And oftentimes in the social sciences, there won't be one, in which case frequentist methods don't apply, even though you're probably listening to someone who is attempting to apply them. But none of the conclusions based on probability will make any sense unless there's some fairly well understood and repeatable randomization being contemplated. And then, assuming that there is, all the probability, question.
Is random sample or random assignment to the treatment?
Or both. Or, if we're talking about shuffling cards and dealing from the top, just, whatever that mechanism is. And then the probability statements that are made are all looking forward from the instant right before the randomization happens. And they're conditioning on everything that's like backward in time from that, including the parameters. And this is what strikes me and a lot of other people as a weird framework to then use in order to estimate or to make inferences or to make decisions on the basis of estimates of theta, because you're setting up all the probability to be, the probability of something conditional on the parameters. So how could you then turn around and use that to estimate the parameters or make inferences about the parameters? It's sort of a very contorted framework for thinking about things empirically, even though it sort of makes sense mathematically. Next tip, only make probability statements about random variables, namely data or functions of data, such as estimators, or estimators are functions of data, and test statistics, which are usually functions of estimators. So all of those have probability distributions induced by the randomization mechanism. The data could have been different, in which case the estimate would have been different, in which case the test statistic would have been different. But across all the ways that you could have done the randomization, then there's this distribution of estimates or test statistics or whatever that we can describe with probability distributions like this one, or the normal, or the chi-squared, or whatever. But don't make probability statements about constants that you conditioned on, namely the parameters, your research hypothesis, anything about the research design. Those are all fixed constants at the time of the randomization, and therefore all the probability statements are conditional on those, rather than being able to make probability statements about theta, or to say that based on the data your hypothesis is probably true. None of those are admissible statements under the frequentist way of looking at probability, because those are all things that are, conditioned on rather than being treated as random variables. Another helpful trick that Bayesians have been saying for a long time that people don't really do. So instead of saying the probability of like something, in which case it might be not super clear whether you're making a frequentist statement or a Bayesian statement or something else. So if you're trying to make a frequentist statement, just say the proportion of times that A would happen over the randomizations. Those additional randomizations are usually entirely hypothetical, but that's what the frequentist probability is saying in like long words. Conversely, if you're making a Bayesian statement, then say, my belief that A is true is described by this probability distribution. And so the fact that both Bayesians and frequentists use probability as a shorthand for different concepts, I think perpetuates the confusion, even though the rules of probability are the same, irrespective of how you interpret it or how you are applying it. Another thing along the same lines, frequentists have all kinds of buzzwords where they take a word that means like something pretty uncontroversial in English, and then they give it a different definition when used in a statistics or probability context. So instead of using the buzzwords, which even if you understand what they mean, whoever you're talking to most likely doesn't. So instead of saying, okay, this estimator is unbiased, say the average of this estimator across random samples of size n is equal to the parameter we're trying to estimate. That is just a long way of saying an estimator is unbiased, but it's more clear what it is you mean, and it's more clear that you are making a frequentist statement because you're referring to a function of data across all the different ways that you could have taken a random sample of size n from your population. Another thing I didn't write up here, but it's good to remember that our populations are usually technically finite, even if they're very huge. To make the calculations easier, we often assume like continuous probability distributions and like an infinite population or whatever, but that's just to facilitate the calculation. That doesn't really help the intuition of thinking about what does probability mean from the frequentist perspective. So if you think about there's this huge but finite population, and I take a small but finite sample from that population, all like something choose something ways that I could have done that is going to have a different corresponding estimate of this parameter, and the collection of those is a probability distribution of the estimator, and I can say probability statements about that. Also, finally, frequentist methods, not only do they not produce a distribution of beliefs about unknowns, they deliberately don't do that. They were created because they thought a distribution of beliefs was a bad thing. It was an insufficient foundation for science if two different scientists can believe two different things after seeing the same data. Particularly like 100 years ago, that was thought to be like unfathomable. But it's actually just kind of like the way the world works, irrespective of like how much you try to make people follow the frequentist rules. People are going to believe different things. And so the Bayesian approach is essentially, okay, how do we deal with that? All right. So an example of, some math is an example. So Bayesians are really interested in expectations of functions that take the following form. So G is some function of the parameters, maybe a utility function that you're going to get the expectation of in order to decide what decision would maximize your utility. And then you have a posterior PDF of these parameters given the observed data that you have collected. And you're interested in the expectation of this G function, which is the integral across the parameter space, all the dimensions of theta of the G function weighted by the posterior PDF. So you integrate theta out of that and you have your expectation of utility or whatever the G function is. May not be able to do that integral in the elementary form. In fact, most often you cannot. But that's the sort of conceptual quantity that Bayesians are interested in, an expectation over the parameters of some function of interest. In contrast, frequentists are ultimately interested in expectations of a different function, but moreover, they're using a different density function to weight. So h is some function of the data, like an estimator, and then the density function they're using is the conditional density function of the data given the parameters, and then they're integrating that out over omega, the sample space of observable data, all in dimensions of that if you have n data points in your research design. H could also be an interval estimator or whatnot. If it were an interval estimator, then you would want this expectation to come out to be exactly 0.95 or whatever intervals you want to capture the true population parameter with across all the different ways that you could have taken in observations from this population. And there's a lot of people out there who profess to be skilled quantitative analysts who would look at this slide and say, well, those are basically the same thing. In both cases, you're taking an integral, and in both cases, I don't know how to do that integral. So what's the difference? Well, the g function is different from the h function. The f functions are different. One is a posterior PDF for the parameters conditional on the data. The other is a PDF for the data conditional on the parameters. So even though they both involve the letter f, they're different functions. And you're integrating them over different things. The Bayesian is going to integrate this over parameters. Frequentist is going to integrate this over observable data. So from a mathematical perspective, they have nothing in common. And they're used in different ways. So bear that in mind. And let's do an example of sort of a frequentist way of doing simulations in order to analyze an estimator. So if we have this is an example from Lancaster in the reading. If we have an autoregressive process, that's y at time t is equal to y at times t minus 1 multiplied by a coefficient rho, maybe shifted over by an intercept alpha. Alpha can be represented as mu times 1 minus rho if rho is less than 1 in absolute value, where mu is the marginal expectation of the outcome. And then epsilon are error terms, which are ordinarily assumed to be distributed normally with the expectation of 0 and some unknown, at least to us, standard deviation sigma. Okay, and if then we wanted to analyze what are the properties of the ordinary least squares estimator in this case of that slope coefficient, and we want to estimate we want to find out about the properties of the OLS estimator across all data sets of size t that we might be able to obtain for a process like this, then our function to accomplish that would be written like this. First, S, the number of simulations we want to do, that is like some large integer. And then these other things, t, mu, rho, sigma, these are all scalars that you have to pass from the outside to this function. And we're going to do everything conditional on those 4 values that you choose. Okay, t, whatever, we'll call that like 50. Mu can be, something, rho can be something between -1 and 1, and sigma can be something positive. But you have to fix those values because we're doing the simulation conditional on those parameter values. So I can just allocate a vector to hold my slope estimates. I'll calculate alpha one time is mu times 1 minus rho, loop over all the simulations that I want to do, allocate me a vector of outcomes, put like a 0 in the first place just to condition on it. Then from 2 up to t, I'm going to use the autoregressive process to generate the data. with random error terms that have a standard deviation of sigma. And once I have those 50 observations, I'm going to use the LM function to estimate the outcome as a function of its lag. And then there'll also be an intercept in there. But I'll take the second element of the coefficients, which is the slope, and I'll just stick that into my collection of estimates of rho. And then when that loop over S is done, then I'll return them out at the end. So the important points to remember here is, one, all the parameters, they have fixed values and they're passed in exogenously from the outside. We're evaluating this over data sets that could have been created by this process. And for each data set, we're applying some function to it in order to get out an estimate, in this case, an OLS estimate of rho. And so by doing this for large S, we can then get a probability distribution of estimates, and then we can say stuff about that probability distribution, which we'll do next, unless there's some questions. Okay. All right. So we do that like 10,000 times with a rho of 0.9 and a sigma of 1, and we get out a probability distribution of estimates that, you know, can be smoothed out like this with the black line. And I've put a vertical red line at 0.9 to indicate the true value of rho that we generated the data with. And so then sort of the main frequentist thing is to say, okay, what are the properties of the probability distribution represented by the black line here, this collection of estimates of the same rho, which was 0.9, but every time we do it with random data, we get, you know, a slightly different estimate. And you can see in this case, the ordinary least squares estimator of rho is not a particularly good one. The bulk of the estimates are too low, and so the ordinary least squared estimator is biased downward in the usual case in the social science where rho is positive, because the expectation of the estimator, which is given by this function, weighted by the probability of the data given the parameters, is not equal to the true parameter that we're trying to estimate. Now, there's certainly other estimators that are better, but the point I'm trying to make here is this is how you would go about doing a frequentist analysis of the estimator, not, you know, of any particular estimate or you know, in any, you know, particular circumstance. We're just saying, okay, the properties of this estimator across data sets are not so great for this estimator. Also, occasionally it's greater than, the estimate is greater than 1, which is, you know, impossible for a stationary process. So that's not great either. So anyway, there's better estimators, but this is like a very core frequentist thing to do. When you're proposing a new estimator, you have to usually do simulations of the data generating process conditional on the parameters in order to evaluate whether the collection of estimates is good as a whole. So it's very much about the forest rather than the trees. When you're doing your own research, you're interested in the tree, like one tree, your estimate of the thing that you care about, not like I'm going to do this 10,000 times. Right? Questions about that? Right, and basically, like, the idea of frequentism, like, if there could be some rule that would make all scientists, you know, use this or that estimator in this situation, then science as a whole, I wouldn't necessarily say it's on good footing, but we would know the properties of science as a whole if they were to use like this estimator in this circumstance across all data sets that a scientist might collect that pertain to that circumstance. So it's very much sort of about suggesting strongly these policies for how research should be done. And in any particular case, we don't know whether the estimate is good, but we know it comes from a process whose properties are known, whether those properties are good or bad. But as you might, those of you who've studied some political science or economics or whatever, what's the incentive for an individual researcher to adhere to this policy? If it's not much, if they have some other incentives, then it's not really clear that you're going to get these good properties as a whole if every individual time people have incentives to deviate from the policy. And you see that a lot in research, both like good deviations and bad deviations. All right. So how would we maybe do more of a Bayesian thing? So back to this data set of the number of soldiers in the Prussian army in like the 1800s killed by being kicked by their own horses, which I don't know why that was such a big problem. You'd think the first person to get killed would serve as an example for the other people to not like walk up behind a horse, in which case, it wouldn't be a persistent problem. But anyway, so the outcome is a count. Maybe the Poisson would be reasonable for the conditional distribution given the unknown mu, but we don't know what mu is. We do know that it has to be positive. And so we can use the inverse CDF transformation from the 0-1 interval to enforce that using the same Johnson quantile parameterized distribution of a semi-bounded random variable that we did before with income, but now we're doing it with mu. So we can encode the 25th percentile, the median, and the 75th percentile to be whatever we want. I did 0.51 and 1.75. Get the data set from the PSCL package. And then the numerator of Bayes' rule can be evaluated for any p and the observed y and whatever specified quantiles I want by evaluating this transformation to get mu, and then using the Dupois function for the likelihood of mu, again evaluated only at the data points that we have, but potentially evaluated at any positive mu. Those are going to be small numbers, so I work in logarithms, and I have to take the sum over the columns. This turns out to be a matrix because the integrate function will pass a vector to p, and so for every value of p there's a mu, and for every mu there's a vector of n counts for the number of deaths by horse kick, so it comes out to be a matrix when I s-apply this, and so I want to sum over the columns to get the log likelihood for the entire data set, and then I exp that to get it back into probability form. And when I do, so that's my numerator of Bayes' rule. When I integrate the numerator to get the denominator from 0 to 1, because that's the space of p, I get back a number that is extremely small. So the probability of observing the data is on the order of 2 times 10 to the negative 138. But there's like 40 observations on each, like 40 years of data on 7 divisions of the Prussian army. So there's 280 data points total. This is saying the probability of observing exactly those 280 numbers in sequence is, real small. But that's going to basically be the case for all data sets that are not like tiny, like the Ebola one. The probability of observing exactly your data set is always going to be like a really small number. That's why if we were to try to calculate it, we have to be really careful about, use the logarithms and stuff like that. Okay, so if this is the denominator, the probability of observing the data, it seems as if the algorithm that we talked about on Tuesday of matching with the prior predictive distribution in order to get draws from the posterior distribution is going to be horribly inefficient. We're going to reject essentially all proposals for mu because there's an almost zero chance of exactly matching the data row by row. So when we did it with Ebola, we just had one thing that we had to match with. In principle, if we were going to do it this way, we would have to match 180 observations exactly with our simulations. So that's not going to, generalize very well. We can use one trick, which actually gets us by in this case, and that is to note that the sum of n Poisson distributed random variables that have the same expectation is also going to be Poisson, and now the expectation is n times mu. So the sum of the deaths by horse kick over the data set should be distributed Poisson with expectation n times mu if our model is correct. And we can utilize this fact to get a much more auspicious algorithm. So n is like 280, y is 186 or something like that. Want to do 4,000 simulations, and I allocate myself a vector of mu's. Loop over S, get a proposal for mu by sticking in a random draw from the standard uniform distribution into the Johnson quantile parameterized distribution that's semi-bounded. Specify my lower bound of 0, my quartile is at 0.25, and then this vector of 3 numbers that specifies what I thought under the prior. That's my proposal for mu. I use that proposal for mu after multiplying it by n in order to get a draw for the sum of the number of deaths by horse kick over the entire data set, y underscore. And if that exactly matches my observed y, which I think was 186 or something like that, then I'm going to keep my realization of mu in increment s. Otherwise, do nothing, just keep repeating the loop until I've filled up a whole vector of 4,000. And that eventually terminates. Actually, it's only like 20 seconds, so it's not that bad. And then when I compare the summary of my posterior distribution of mu to my prior quantiles, I see that having observed the data, my updated beliefs are that this is less frequent than what I thought in my prior. Posterior mean, posterior median are all about 0.7, which is close to the sample average in the data. And the first quartile and the third quartile are pretty close to the median, in contrast to what I had before, where everything was more spread out and maybe shifted more to the right. So I've updated my beliefs about mu. Right? So the same process, really, we were talking about on Tuesday, just using the semi-bounded inverse CDF rather than the bounded on both sides version of the same thing, but it essentially required the same amount of effort for me, the researcher, to specify those 3 quantiles to characterize my prior beliefs about mu before I saw the data. Questions?
So when Bayesians, like when they don't think of like the parameter as like a constant value in the world, is it like some kind of philosophical position that like there is no one like constant of gravity in sort of senses because everything is changing all the time and everything? Or is it just because like you could imagine with like a lot of data converging to probability distribution with like 100% of chance of like the parameter being this value? So is it a problem of the data, or is it a problem with like the world and everything changing according to space and time?
So it's a problem with the world if you think of your task as trying to get every last detail right. But models are not really trying to get every last detail right. They're trying to give simplification of the process that still preserves the insight that we want to make and gives us a posterior distribution that we can use to make conclusions and decisions and things like that. So what you might say is, well, each horse has a different propensity to get startled and kick whatever is behind it. And so there should be a different mu for each horse. But like somebody who collected the data set didn't collect it on a horse by horse basis. So there was really no information on the data set to estimate a horse specific mu. Now you can kind of do it in the Bayesian sense. It's just conditional on data that aggregates over all horses, you wouldn't really update your beliefs about, snowball, because you don't have any snowball specific data. So you're really just left with like whatever your prior is as to how like violent snowball is.
And so what is the n, if I remember correctly? N, like it says like number of rows, and the rows are years, right? Is that?
Yeah, except that they have 7 different divisions of the Prussian army, so it's stacked up. Years, 7 divisions, something like that.
Sorry, this is from the last slide, but I see why the denominator ends up being super low, like given sort of like what the structure of the data looks like. But like if you have like continuous data, like shouldn't it be 0?
Right. So in the case you have, the denominator is a density rather than a PMF, and so the probability of observing your data set is 0, but it has a probability density. In this case, there are discrete deaths, so there is a actual probability of observing this data set. It's just so close to 0 that like, whatever. Okay. So if we were to use the so-called gamma prior, we could get an exact posterior distribution without having to do prior predictive matching or MCMC of any kind. I should also mention, like, Stan doesn't care about this. So Stan basically just works off the numerator. So that can be like as ridiculously close to 0 as you want. Stan would have no problem with this. But if we didn't have Stan, and maybe it was a little bit worse, we couldn't do prior predictive matching. If we change the prior, we could get an exact result. So the PDF of the gamma distribution is given in red here. So this is what we're going to use for our prior on mu. It depends on 2 hyperparameters A and B that have to be positive. And one fun fact about the gamma distribution is its expectation is equal to A over B. So you could choose A over B to be in line with what you think. Probably something pretty small in this case, but that only pins down their ratio. To think about exactly what to do for A and B, you'd have to think about the variance or something like that. Then before you observe the data, the Poisson PMF for n observations can be written like this in the middle, but observe that we can simplify like all this product by pulling out the e, and then we have mu, and it's going to have the sum of the y's and the exponent. And then the only thing that we actually have to have a product over is this ratio of factorials. But when we consider that same expression to be a likelihood function of mu, so after we observe the data and we're only evaluating this at the data we observe, then the likelihood function, we can actually ignore constants that only involve y and just keep the kernel that involves mu. And so we get a simplified expression for the likelihood function of mu. Then the posterior PDF is going to be proportional to the product of the prior PMF and the likelihood function. And so as we see in this case, the kernel of the prior, the part that involves mu, has the same form as the kernel of the likelihood. So we can simplify these terms and write it basically in the same form as our prior, mu to the a star minus 1 times e to the negative b star times mu, where a star is equal to a plus the sum of the y's, and b star is equal to b plus n. So now we have an expression that the posterior PDF is proportional to, which has the same kernel as our gamma prior. Therefore, the normalizing constant that makes the thing integrate to 1 is just going to be the same as the normalizing constant there, but evaluated at a star and b star rather than a and b. So in the case of gamma prior, Poisson likelihood, the posterior is exactly gamma, but it's going to have updated hyperparameters a star and b star rather than the a and the b that you started with. But for large n, again, this is going to converge to the sample average, finite A and B, right? So, there's a handful of these conjugacy relationships that we can do, but it's not really general enough. So sort of as a preview for like a little bit of the rest, think about 4 ways in which we could like go through the process of updating our beliefs about stuff using Bayes' rule. So one way is to draw from the prior predictive distribution and keep realizations of the parameters if they exactly match the observed outcome that we see from the data. So that is very intuitive. It works great with small counts, but it's only going to be possible in a limited number of situations that we might encounter. Otherwise, the denominator of Bayes' rule is going to get so close to 0 that we almost never match. And so it's not a feasible algorithm in general. We can do numerical integration with like little trapezoids, where we like make some function and then call integrate and then get the denominator of it. That is good in the sense it's more similar to what we did in the discrete case, like on the homework, where like upsilon was weirdly this integer valued unknown rather than a continuous unknown. But basically we had all these like points in the numerator that we could sum up and get the denominator and divide in order to get this posterior distribution. So that is only really feasible when there's 1 or 2 parameters, and even in that case, the numerical integration can be inaccurate if the numerator is like sufficiently complicated. Usually, probability functions are pretty well behaved. So this really is pretty feasible as long as you have 1 or 2 parameters. But doing numerical integration in high dimensions, where high like starts at 3, isn't really deterministic numerical integration is not that feasible when you have more than 1 or 2 dimensions. There are a handful, maybe 20 or so cases where we can say the prior is naturally conjugate with the likelihood, in which we can get an analytical result for the posterior distribution of the parameters. This form is good because it illustrates this idea of Bayesian updating is incremental. There will always be some like A star and B star that depends on like the data in N or whatever. And so it makes it clear that you could update your beliefs like 1 data point at a time, or all N, or in 2 batches or something like that. In the end, you're going to end up with the same posterior distribution after you've observed all the data. But like I said, that is only possible in fairly simple models, that the likelihood comes from the so-called exponential family of distributions, in which case we can choose a prior that has the same kernel. That's usually only going to be feasible with like 1 parameter models, and so not nearly general enough for the sorts of research situations that we want to do in the social sciences. So fourth, you can use Markov chain Monte Carlo, in particular STAN, and that gives you a good chance of being able to successfully sample to obtain draws from the posterior distribution, at least in the case of STAN, for any posterior density function that's differentiable with respect to the parameters, which is a much, much wider class than anything that is feasible or possible under the previous 3 methods mentioned. And we'll start to learn about that next week, the algorithm that Stan uses to do that. So turning to the reading, some important points, I think, from a really good chapter on sort of subjective Bayesian approach in economics, but it applies, I think, throughout the social sciences. One point Lancaster makes is that choosing your prior is not really a fundamentally different process than choosing your likelihood. It doesn't even have to be yours. You can do it on behalf of someone else. It's also not fundamentally different from choosing your utility function. So Fisher and people like him got all upset about the prior being subjective. One person could make a different choice than somebody else. But if we're going to use the results to make decisions, then we're also going to have to bring in a utility function, and that too is going to be, something that one person could subjectively choose in a different way than another person subjectively chooses it. So if this is going to be useful for making conclusions and taking actions as a result of research, there's no way we're going to be able to eliminate all the subjectivity from it. So we might as well have basically Bayes' rule as the guiding principle for how to manage and update those subjective beliefs. Another important point for understanding things and for verifying that your algorithm works, simulated data from the prior predictive distribution is much more useful for that purpose than data that you collect from the wild. Because data that you collect from the wild, it might not work well because the model doesn't actually apply to those data. So for checking things and for understanding things, it's good to simulate data from the model. And so you don't have this gap between what your model is modeling and reality, in order to make sure you understand and that you understand the implications of your prior and how your estimation works, and then you turn it to data that you collect from the wild that you hope was generated by some process that is sufficiently close to the model that you specified. The so-called likelihood principle, the principle that the data that might have been seen but were not are irrelevant to inference. And then he says, somewhat tongue-in-cheek, that professional opinion is divided on whether inference should adhere to the likelihood principle, by which he means Bayesian inference adheres to it and frequentist inference does not. Well, most of Bayesian inference adheres to it. You could choose to not, but in general, Bayesian does and frequentist doesn't, which is this sort of weird, it's another aspect of this sort of weird thing where the frequentist conclusions are driven by these, what would the data look like under, or functions of the data look like if we were to hypothetically repeat this process over and over and over again, where we take in observations from this population as our sample and then apply the estimator to it, get these collection of estimators, and then somehow that yields us a conclusion as what we should do, but it's based on data that we haven't actually observed. Whereas everything with Bayesian is conditional just on the data that you have, and hence it doesn't require that the data be a sample, which is good because often in the social sciences it isn't a sample from a well-defined population. You're making conclusions about the parameters in the data that you have, and if you want to try to generalize it to a larger population, that is a challenge, but that's a different thing than using Bayes' rule to update your beliefs about the parameters, given the data that you have. So your data doesn't have to be like a probability sample from whatever population you're thinking about. Also, it invokes this idea of identification, which I wanted to clarify. So that means there's like two sets of the parameters such that the conditional distribution of the data is going to be the same, irrespective of what the data are. In that situation, we say the parameter theta is not identified. Unfortunately, in my opinion, if you read the Stan documentation or the Stan forums or like blog posts around Stan, there's a lot of people who sort of throw around the word identification in a much looser way. And the way they're saying it is basically means like, this is hard for Stan if it's not identified. Or if it's hard for Stan, then it's not identified, which is like even more like, it's not a real definition. So anyway, this is the actual definition. And if you want to say something's hard for Stan, and we'll encounter situations in which that is true, you want to say more specifically what it is that makes this hard. Is there like a ridge in the likelihood, or like the tails of the posterior distribution are too heavy, they go out too far, or you can multiply a parameter by -1 and it doesn't change the probability of observing the data you see. Those are all like specific things, some of which constitute a lack of identifiability. But anyway, that's a better thing. We should probably wait until we encounter one of those before we get too caught up in that. So the Lancaster chapter ends mostly, with different ways of choosing priors, which, like I've said before, is very historically and still today controversial aspect of Bayesian inference. And I want to talk about a few of these 6 things about ways of thinking about choosing different priors. So the first thing, and Lancaster says it, but maybe not forcefully enough, is that you shouldn't use improper priors. Improper priors are those that have not PDF, because the thing that acts like a PDF doesn't integrate to 1 over the parameter space. And so you can't draw realizations from these priors. You can't use them to kick off a prior predictive distribution. In some cases, not all, it implies the posterior distribution is going to be improper, in which case it's useless for Bayesian inference. If you want to use an improper prior, you have to figure out whether the posterior is proper on a case-by-case basis by doing some algebra and calculus yourself. But sort of, if you avoid improper priors, if you only use proper priors, that is sufficient. You will always get a proper posterior. So that is a very useful, sufficient condition. But even if you don't utilize that sufficient condition, if you use improper priors, you can't do Bayes factors. And usually if you try to use improper prior, even though it's legal in Stan, you'll run into computational problems, and Stan basically says, this is too hard. But that is basically easily fixable by specifying actual prior rather than this improper prior. But there were certainly decades where people thought improper priors were fashionable because they sort of encompass the entire audience, even though they encompass them in a way that's not mathematically valid. Whatever. So what we've emphasized so far, and what we'll continue to emphasize, is so-called subjective priors, where you basically just say what it is you think. Not that that people can disagree with you, but just at least to start with, put what you think. And so we've already covered the case where we can use these inverse CDFs when we have bounds on both sides, or when we have bound just on the lower bound. So here I wanted to sketch out how we would do this in the case the parameter is any real number. And in this situation, there's actually 3 or 4 maybe different approaches. And I'm not entirely sure which one is going to be best in all circumstances. But here I'll talk about one involving the inverse CDF of the so-called generalized lambda distribution, which in this parameterization actually does not involve lambda anywhere. But it is characterized by this inverse CDF that depends on M, R, A, and S. So M is the median, R is the interquartile range, the difference between the 75th percentile quantile and the 25th percentile quantile. So the interquartile range scales up the sort of standard generalized lambda distribution, and then you shift it over by the median. Then we have 2 others, A, which controls the asymmetry of the generalized lambda distribution, and S controls the steepness or the heaviness of the tails. So you can specify a median, a 25th percentile, a 75th percentile, but that only pins down M and R. So you have to, 1, specify an extra quantile, and you're going to have to solve for A and S numerically. And the function is kind of complicated, but I've already implemented it. So if you download that helpers R file from Canvas, and let's say you were in a situation, you have this parameter theta that could be any real number. You think there's an even chance that it's greater than or less than 2, a 25% chance it's less than 0.5, a 75% chance it's less than 3, and then I'm going to need 1 more quantile because I don't have bounds. So let's say a 90th percentile is 5. There's a 90% chance under my prior beliefs that this thing is less than 5. And so it can solve 2 equations for 2 unknowns pretty fast and well. And so we get back the asymmetry and steepness parameters that correspond to the quantiles that I said here. And as we saw before, if I then evaluate the generalized lambda distribution inverse CDF, which is again defined in the quantile_functions.stand program on Canvas, and then I evaluate this at 0.25, 0.5, 0.75, and 0.9, putting in the median, the interquartile range, and the asymmetry and the steepness parameters that I solve for, I get back exactly what I put. So, and that's the same way with the Johnson quantile thing. So basically, this is a relatively easy, fairly transparent, or at least clear, what it is that you're saying, and we can make it work if we have bounded parameters, if we have strictly positive parameters, or we have parameters that are defined for all real numbers. It's basically the same process. It's just when we don't have bounds, we need one extra quantile in order to characterize 4 parameters to the generalized lambda distribution. And this particular prior has tails that are so heavy that the expectation and the variance don't exist. So the integrals that define those expectations don't converge. But the median and the quantiles exist. The distribution exists. So everything is basically fine except for that. So we'll maybe do one thing about maximum entropy distributions and then we'll quit. So another approach to choosing priors is to say, well, what function would maximize the entropy of the results subject to some constraints? And so this is a way that's been used for a long time to choose a family of prior distributions. And so a lot of these I think are not so useful, but 3 that are. So if your parameter space is some convex set, then the maximum entropy distribution is always going to be uniform on that convex set. In particular, if you have the real line, whatever, it'd be standard uniform or whatever uniform. If your parameter space is all real numbers, then the maximum entropy for a given expectation and variance is the normal distribution. And maximum entropy essentially means this distribution conveys the least amount of information above and beyond the information you're provided by specifying the expectation and the variance. So specifying the expectation and the variance provides a lot of information. But the normal has the least information on top of that among all distributions over the entire real line for a particular expectation and variance. So that is one reason why the normal distribution is so commonly used in statistics and science and whatnot. Also, finally, if you have a parameter space that's all positive real numbers, the maximum entropy, which is to say, in a manner of speaking, minimum information or minimum extra information distribution is for a given expectation is the exponential distribution with whatever expectation you want to specify. And you might say, well, it's hard for me to think about the expectation of a distribution that goes off to infinity, particularly if that distribution is asymmetric, because the expectation depends a lot on exactly how fast the tail is going towards 0 in ways that you really don't have a very good intuition about. So with the exponential distribution, it has one parameter, and you can go from saying, okay, here's what I think the median of this is, and then multiply it or divide it by the log of 2, and then you get the expectation. So you can go from median to expectation if you find, like I do, that medians are easier to think about. Quantiles are easier to think about. Anyway, there's a lot of other examples on Wikipedia. Basically, all the famous distributions are a maximum entropy distribution with some constraints on like the expectation and the variance of some usually weird function that you often wouldn't really feel too good about specifying. But that basically go from these expectations of functions, fix those, and then choose the distribution that maximizes entropy is an alternative approach that is definitely historically prevalent. And if you read like Mikhail Reed's stuff, he really loves maximum entropy distributions as well. So question?
Summarize this if I understand it correctly. Maximum entropy distributions are nice because they convey very little information. The least extra information.
Beyond the constraints that you specified. So if I say my expectation of this is 3, that's a lot of information. But like the exponential distribution comes with very little or minimal information above and beyond the expectation is 3.
Okay. And hence they make for a nice prior distribution that we assume, so that our assumptions are non-controversial, and that's why instead of some non-parametric weird distribution that would be fitting our assumptions,
Like this.
yeah, we use uniform so that it's not a controversial prior, so
Right.
we
Well,
don't have
the
to
only
argue about this.
controversy is what constraints. So, fix the expectation. And then, okay, if you have a positive parameter space, then the maximum entropy, minimal extra information is exponential, but the constraint you specified could still be controversial.
All right.
So that's it for today. I will post the second homework tonight. It'll be due before class on Thursday, and it'll involve, doing stuff with continuous random variables. All right. So, same deal. Post on Campus Wire if you have questions about that.